Okay, so this group was composed of a number of students that were split up into separate groups. They all had a separate project that all fed into the Formula SAE race car that we build every year. We build one from scratch, and we race it in May in Michigan. And for the past 3 years, we've had high school students attack these problems that ultimately do find their way on the race car itself. It's a full-size race car, if anybody asks, and yes, students do drive it, and yes, it goes pretty fast. So without any further ado, go ahead, guys.
Good morning. This is race car design. Every year, there's a competition between 120 colleges and universities from around the nation and the world, where teams of students design and construct Formula-style race cars. There are two main components to the Formula SAE competition: the design aspect and the racing aspect. Through numerous events and tests during the competition, each vehicle is given a score and a rank. Every year, the students who are part of the Cooper Union Motorsports team research, design, and construct a race car from scratch. For the past 6 weeks here at the Cooper Union Summer STEM program, 6 groups have been working on 6 different components that could potentially be placed on the race car. And here is all of their hard work. Today, we will be presenting to you the Helmholtz resonator. My name is Evan Strauss.
I'm Kelly Sakaguchi.
I'm Sterling Cohen. And I'm Raul Ramirez.
During the Formula SAE competition, one of the events is the sound test, where it is necessary to run the engine at a certain speed and have the sound output level below 110 decibels. To decrease the sound output, the current design has metal mesh that is attached to the end of the tailpipe. However, the problem with this current design is that the power that could be transmitted from the engine to the wheels is instead used to push out exhaust gases from the tailpipe. The goal of our project was to create an alternative solution to pass the sound test, and we did this by researching, designing, and constructing a Helmholtz resonator.
A Helmholtz resonator is a device intended to attenuate or decrease noise. It's comprised of a hollow resonator body and a neck, which is attached perpendicular to the exhaust coming out of the engine. It functions similar to a spring. Just as a spring oscillates up and down, the air in the neck of a resonator also moves up and down. The rate at which this air moves up and down is the resonant frequency of the resonator, and is dependent on both the frequency that's being played through the exhaust pipe and the dimensions of the resonator body and the resonator neck.
In a car, an exhaust system works to push gas and fuel and air away from the engine, and it does this in a pulsing manner, as we had a graphic here with a piston and gas particles that would move in pulses. During the sound test, it is necessary to have the engine run at 10,500 revolutions per minute. And here we had a conversion that every second, there would be 350 of these exhaust pulses. From this information, we understood that the resonant frequency of our resonator had to be 350 hertz.
So we have an evolution for the Helmholtz resonator. First, we designed a resonator using SOLIDWORKS, and SOLIDWORKS is a computer application to design dimensions for 3D objects such as the Helmholtz resonator. Then we made our resonator come to life by making the cardboard cylinder and the metal neck, which are attached together. Then we upgraded our resonator by making a resonator out of plastic cylinder and a plastic handle. And the handle is used to adjust the volume so that it adjusts the resonant frequency. And this is our current design, which is 3D printed. So this is a 3D printed cylinder, a neck, and the handle.
For our experiment, we generated specific frequencies with a speaker, and as the sound traveled through a tube, we adjusted the plunger and changed the volume or size of a resonator. And with that, we measured the changes in sound level with a sound meter. Next, if it worked, would be an example of what it looks like when the resonator changes size or volume. The sound meter also changes. We would adjust the volume of the resonator to a specific point where the resonant frequency of the resonator matches the frequency of the sound. Next would have been a graph with frequency on the x-axis, or pitch, and the decibels on the y-axis, or how loud the sound is. What we learned is that our resonator did not attenuate or dampen every frequency. In fact, when we changed the resonator to different volumes or sizes, it attenuated or dampened specific frequencies.
Through our experiments, we determined that qualitatively the theory was fairly accurate. When we increased the volume, the frequency that the noise level was most decreased at decreased, and the range of frequencies that were attenuated broadened, just as the theory predicted. Quantitatively, however, the theory was quite far off. The frequencies that were predicted to be most attenuated and what we found in our experiments differed by almost 50%. We currently don't have enough institutional knowledge to build a resonator to put onto the car that would effectively attenuate the range of frequencies that the engine produces to pass the noise test. The FSAE team will have to continue to work on this project before these goals are achieved. Thank you.
Sorry, 2-minute break so we can figure out what these technical difficulties are about.
into like incognito?
In what?
Incognito mode, then like
Oh, yeah. You know how to do that one. Just puzzle these guys. Oh, I shut the wire, that's actually. I mean, which is the person that has to leave her?
I don't know which. It's just which computer which has to look. Yeah, I open incognito at once on your.
Oh my gosh, what is wrong with me? You want to do...
It's like a new. I have to make a new tab, a new window. That's yeah. Hunter. Yeah. Is that?
Sometimes you just need to review. Your presentations at the library.
Good morning. To begin, we would like to introduce ourselves. My name is Alani Vargas.
My name is Brittany Ron.
I'm Keely Myers. And I'm Nazim Chowdhury.
And today we will be presenting our carbon fiber steering wheel.
The problems with our current steering wheel is that it is very heavy, and we want the car to be as light as possible. Also, it is not original in that someone else manufactured it for us. And it is made out of aluminum, and that doesn't allow us to customize it the way we want to. We will fix this by making it under a pound using carbon fiber, and we will make it ourselves using our own design.
As a team, we hope to implement our steering wheel onto the race car. By improving the manufacturing process of layup for carbon fiber, we want to end up with a product that not only meets the requirements, but has a clean and smooth finish. And by improving the consistency of these layup techniques, it means that the rest of the group and the other sections of the car will be able to use this technique and be successful with any future carbon fiber layups. To achieve our goals, our group decided to create the carbon fiber steering wheel using a fiberglass mold. For the mold, we sent a computer design to the CNC router in order for it to cut an exact copy of the steering wheel design. Once we had the foam in the shape of the wheel, we then sanded and waxed it in order to have a non-porous surface. With the non-porous surface, we're able to apply and remove the orange gel coat with ease. Once the orange gel coat has dried on the surface, we apply 4 layers of fiberglass with epoxy in order to reinforce the mold. Once the mold is cured, we then remove the foam and wet sand it inside in order to have a near mirror finish. The last step of manufacturing the mold is to wax it so it will be ready to release once we use it on the carbon fiber wheel.
Our carbon fiber wheel consists of a blue polystyrene foam core that is cut from a CNC router. This foam core is then placed in between pre-cut patterns of carbon fiber and is saturated with an epoxy resin system. This is done in order to properly adhere the carbon fiber to the foam core. It is then placed inside of our fiberglass mold for a clean mirror finish. Once cured, the wheel is removed from the mold and is sanded so that the driver can safely grip the wheel and drive the new wheel. Yeah.
We then put our wheel into an Inchon machine to test the tensile strength. The Inchon machine is a device that evaluates the mechanical properties of an object using compression, stretching, impact, and so on. It also gives us statistical data as it is functioning. So after we turned off the Inchon machine, we observed that the wheel itself did not break, but because it bent so much, we believe the inside core did. In the graph, we plotted a dotted line to show the minimum load a wheel should withstand in the competition according to Formula SAE rules. Our R wheel, however, in the red line, shows that we far exceeded the requirement.
In conclusion, we have made tremendous progress over the last 6 weeks. One of our biggest accomplishments was that we made it easier to replicate a carbon fiber steering wheel. We developed a layup technique that revolves around a fiberglass mold that is reusable. Also, the carbon fiber layup process impacts and is useful for future work on multiple parts of the race car. We also set a standard for weight reduction, and we reduced the weight of our new wheel by over 80%. The new techniques we've implemented and our work with complex composites will leave a lasting effect for the Formula Race Car team this upcoming year. Thank you for your time.
Good morning. We are the Adjustable Pedal Set Group. My name is Bill Huang. My name is Jin Lee. I'm Gavri Kapetz.
I'm Tyler Young. So the main objective of our experiment was to redesign the pedal set to increase the drivability for the mid-sized drivers. As you can see, the current pedal set are rough. We can see the clutch pedal, the brake pedal, the throttle, and the footrest. In our experiment, we mainly wanted to focus on adjustability and ergonomics in order to see the increase of drivability for the inside drivers. We created experiments to test the different footrest. We created experiments to test drivability by measuring footrest height, footrest angles, we created an experiment to test the different size drivers. We created an experiment to test drivability of different size drivers. And the reaction time, driver comfort, and the ergonomics. We tested driver comfort by measuring footrest positions, footrest angles, and footrest heights. We tested different angles by creating a small method footrest shape with angles 36 degrees, 60 degrees, and 75 degrees.
For our experiment, we created a computer program that records the driver height, the driver reaction time, and the driver comfort rate for each pedal position. In order to test the reaction time, we put a mouse under the throttle pedal, and when prompted with a red screen, the user pushes down on the pedal, which clicks the mouse, and records the reaction time. From this experiment, we learned that different drivers of different heights did prefer certain pedal sets and pedal positions. And we also learned that the lower footrest did benefit most of the drivers. Following the experiment, we created a on-the-go adjustable brake pedal. So the rules on the FSAE rulebook say that it has to withstand 2,000 newtons of force, and it also has to be made out of certain metals. We chose titanium for its good ratio of stiffness to weight. On your right-hand side, you'll see a CAD that we made. You'll see the different parts of the pedal. So the upper arm is highlighted in red, and the lower arm is made gold. And so the red upper arm will rotate around the pivot point between those two arms and allow different pedal face positions. So in the left-hand corner, you'll see a 3D printed mock-up that we made for this pedal. And the positions for the pedal were found in the experiment that we did earlier. Here you'll see an exploded image of our pedal, so you can familiarize yourself with the different parts of it. You'll see the upper and lower arm and pedal face. Around the middle, you'll see a bunch of tiny little parts, and that is for the pin mechanism. So the pin mechanism is what keeps the pedal face and upper arm locked in place so you can actually use the pedal. You'll see a plumber pin that goes in and out of a hole, which will lock the system when it's inside the hole and unlock when it's outside, and it's pressed in by a spring. Because
the throttle and clutch pedal do not require any specific load or material, we decided to make it out of carbon fiber, which is light and retain the specific stiffness. We also had different angle setup as it requires a wider range of adjustability. Here is the comparison of our original footrest and our new footrest. Our original footrest is made of aluminum, which is a lot heavier than the new footrest, which is carbon fiber. We decided the angles 36 degrees and 60 degrees for our new footrest based on the experiment mentioned before. Here's our final prototype, but more work needs to be done. It provides a good base for future pedal setups that the race car will need. Thank you for your time.
We are Impact Attenuator. My name is Eduardo Quiroga. I'm Malachi Barrow.
I'm Leona Lau.
I'm Brian Lee.
So Formula SAE requires every team to have an impact attenuator. An impact attenuator is basically a device that absorbs energy during a head-on collision. In order to prevent severe driver whiplash, FSAE set these requirements that each team must meet in order to compete. Our goal is to make a lighter impact attenuator that still fulfills these requirements.
So first we took a look at the previous impact attenuator we had, and of course, like all impact attenuators, it goes on the front of the car, right on top of the bulkhead. It was comprised of seven layers that were separated by 6 aluminum sheets. They all used honeycomb layers, and we decided we're going to use carbon fiber for our overall new impact attenuator, but we still wanted to keep the honeycomb structure so far because it has significant benefits in terms of its strength. And then we wanted to also test the honeycomb structure, which is what you see in the second picture, to make sure that the strength would still hold up. And then we did research on, has anyone else done a carbon fiber nose cone or impact attenuator? And we found that someone else has, and then that's where we found that it has significant shattering properties.
One method that we used to create the carbon fiber honeycombs was using a foam mold. We used a CNC machine to cut a piece of foam out into the shape of our mold. And we then laid up carbon fiber onto the foam mold. And in order to separate the carbon fiber from the foam mold, we just dissolved away all the foam using acetone. Another method that we used was using a fiberglass mold. And to do this, we used a foam mold and then covered it in a layer of gel coat in order to give it a smoother surface. We then laid up the fiberglass on it and waited for it to dry. After that, we separated the fiberglass from the foam, giving us a reusable fiberglass mold that we can use for carbon fiber layups.
We tested our final product in a quasi-static environment using the Instron machine. The Instron crushed at a slow speed of 1/4 of a millimeter per second, and as you can see in the GIF, the carbon fiber honeycomb is slowly folding upon itself. In the future, we plan to test in a more dynamic setting, which will allow for the shattering properties of carbon fiber to show and possibly changing the amount of energy absorbed.
So from that experiment, we used our data extension versus load. The equation on your screen shows the energy absorbed, which is basically the area under the graph. And here we also compare the aluminum versus the carbon fiber, the aluminum meaning the previous impact attenuator and the carbon fiber meaning ours. So clearly the energy absorbed by ours was significantly less. However, it was also 2 times lighter, which is a very big benefit to ours. Still, we need to make several more changes in order for it to compare to the energy per weight. So if we had more time, we have to figure 3 aspects. 1, density, 2, wall thickness, and then 3, crush speed. So density refers to the amount of honeycombs per layer. The one in the aluminum, the previous one, has a lot more honeycombs than ours does, since the carbon fiber one has a height of 0.5 inches. Then the wall thickness, we only use 1 layer of carbon fiber, which is a lot less than what we should have. We should have used a lot more layers. And then finally, crush speed, as Liana mentioned, it was only 0.25 millimeters per second, and to really realistically determine how well it would work, we have to use crash speeds in order to determine. Thank you. morning, everyone. We're the Diffuser Group. My name is Jae Young Cho.
I'm Jack Wilco.
I'm Maddie Huang.
And I'm Evan Zauderer.
So what is a diffuser? A diffuser, by definition, is part of the undertray of a car, which is part of the aerodynamic particle. Its primary goal is to increase the downforce on the rear wheel of the car by changing the pressure. As you can see, under the middle of the car, the air has high velocity, thus creating low pressure. However, as the air passes through the diffuser, it loses velocity, thus creating higher pressure. Because the pressure under the car is lower than the pressure around the car, it creates downforce. This effect is also known as the Venturi effect. In order to make an ideal diffuser, we researched several aspects of it, including the height, the angle, the shape, the core, and the mounting. Based on our height of our car, in order to maximize the downforce, we concluded that an angle of 9 degrees would be ideal for our diffuser.
So before we could get to the wind tunnel testing, we had to first make the models of our diffuser. We started by making foam molds of the two diffuser shapes we were testing, one having rectangular diffusers and the other that has diffusers that taper off towards the front of the diffuser, creating a trapezoidal shape. After we made the molds, we did the carbon fiber layups using the vacuum bag method, and after those were dried, we sanded and trimmed the diffusers to the size we needed for the wind tunnel testing.
So we took these prototypes and put them into the wind tunnel and attached them using strings on all 4 corners and screwed them into the ceiling. We also made an aluminum shield to direct the wind towards the bottom of the diffuser to simulate the airflow if the diffuser was attached to a race car. So these are the 2 diffusers in the wind tunnel. The top one is the rectangular diffusers, and the bottom one's the trapezoidal diffuser. And the wind tunnel can simulate up to 80 miles per hour of air. But the race car doesn't go that fast, but it does prove that the diffusers create downforce.
So we were thinking about different ways that we can get quantitative data from the wind tunnel. We found out we could do this using a sting balance. A sting balance is a device that is able to calculate the force exerted onto it, or in our case, the downforce exerted onto it by the diffuser. So what we did is we connected the diffuser to the sting balance so that whenever the diffuser would be pulled down on by the downforce, the sting balance would also be pulled down upon. However, with this sting balance, we had many problems involving the electronics. So in the end, we had to make a new experiment. A new experiment involved 2 scales and 2 rods. The 2 scales were placed underneath the wind tunnel, and the 2 rods were placed on the scales, touching the diffuser. Therefore, when the diffuser would be pulled down by the downforce, the rods would be pushed down onto the scale, showing the amount of downforce created by the diffuser. From this experiment, we found out that the diffuser that had rectangular diffusers exerted 1 pound of downforce at 90 miles per hour winds, while the diffuser that had trapezoidal diffusers exerted 2.6 pounds of downforce. This was surprising because in other testings, we found out that it looked like that diffuser with rectangular diffusers actually did better, especially since the diffuser with trapezoidal diffusers had shook a lot inside the wind tunnel. For the future, we plan to fix the sting balance since that is a more accurate way to figure out which diffuser is better. Also, we plan to make a diffuser that would actually be able to fit on a Formula race car at Cooper Union. Thank you.
Hello everyone, this is the Electronic Throttle Control Project, and I am John Panagiotopoulos.
I'm Arjun Madan.
I'm Aaron Chen.
I'm Jonathan Morales. So here's the current system on our car. Here we have the throttle body. It controls the air intake into the engine, which also controls engine speed. So let's start with the driver. As the driver pushes down the pedal, the throttle cable on the right is pulled. As the throttle cable is pulled, the throttle valve in the middle is actuated, so it opens and closes. So on the left of the screen, we have the TPS, or throttle position sensor, which feeds the real-time position of the throttle to the ECU, or engine control unit, on the car.
So there were multiple problems with the mechanical throttle control. One of them was delay between the time the driver presses the pedal and the throttle responds due to the friction between the sheathing and the cable. The other one was that the cable itself could be fatigued over time, and the system itself was very hard to maintain and and replaced as the cable traveled through the internal components of the car, which made it very hard to reach.
So our solution to this problem is an electronic throttle control, and what this system does is it removes all mechanical connections and replaces them with electrical components. This removes friction and any delays from fatiguing or braking. Now, the fundamentals of this system are made of 4 key components. The first is the pedal position sensor, which takes the location of the pedal from the driver's foot, from how parts are being pressed, and it sends that information over to the ECU. The ECU is the engine control unit. It is the car's computer. All electrical components run through this and are processed via this. This system then sends information from the sensor on the pedal to the throttle motor, which is what now actuates the throttle valve instead of the cable. And as on the previous system, we have a throttle position sensor that constantly feeds back the lifetime location of our motor.
So, this is the ETC setup that we came up with and implemented on the car. On the top of the screen is the pedal position sensor. We used a rotary potentiometer, which means that as the pedal is pressed and released, the rotary potentiometer turns and sends a different signal to the computer we have in the car. For our computer, we use an Arduino board for simplicity. The Arduino then interprets that signal and sends another signal over to our throttle motor. We use the stepper motor in this case. The stepper motor opens and closes the throttle valve. Finally, we have the TPS, throttle position sensor, which feeds a real-time position of where exactly the throttle is back to the Arduino. Our specific system works in a certain way. The Arduino is constantly comparing the values that it's getting from the TPS to the values from the pedal position sensor. So essentially what that means is that it's comparing where the throttle is at any given time to where the driver wants it to be, depending on where his or her foot is. For example, if the throttle is fully closed and the driver suddenly floors the pedal, the Arduino will notice the difference and correct by opening up the throttle fully. There are 2 major plans that we are planning to add to this project in the future. First, we need to actually program the ECU rather than just having an Arduino do the work. We did an Arduino for this setup for simplicity and because the interface was easier to work with. And second, we would mount the actual throttle on the air intake manifold rather than having it here isolated. Thank you for your time.
Thank you for watching our presentations, and we hope you enjoyed them. Once again, the goal of this program was to improve the design and drivability of the race car, and we hope that all of these components can possibly be put on the vehicle. We would like to thank Professor Delagrammaticus, our teaching assistants, Hunter, Mike, Eric, Dewan, Simon, and Billy. We'd also like to thank Estuardo, Brian, Sinisa, Con Edison, the New York Building Congress, and the Albert Nurkin School of Engineering. Thank you.